Alright, let's look at Rolle's theorem here. Get our slideshow going. Rolle's theorem. First, look at the hypothesis. F of x, any function, needs to be continuous on some closed interval. Okay, so we want the interval to be closed on both ends. We don't want an opening there. We want there actually to be something on those endpoints, as later we see when we look at example. So basically, that just means we don't want an open circle on the end of our interval. It needs to be differentiable. Actually, on the open interval, it's okay if you're not if you can't establish a tangent line on the endpoint, as we see, and that's a small detail, but we do need the endpoints to be there. We just don't have to establish the fact that it's differentiable there. And Rolle's theorem, as later we'll see, is just a special case of the mean value theorem. And the first two bullets of the hypothesis is the same for both theorems, but Rolle's theorem specifically, we want the endpoints to have the same y value. Okay, so you can lay a horizontal line and it goes through both endpoints. If all this is true, then there's going to be some value c in the open interval. Now, it's not an endpoint, but actually between a and b, exclusive, such that the derivative is equal to 0. In other words, you can draw a horizontal derivative, horizontal tangent line through there. And we're going to look at an example and actually physically see that. But here's what they may ask you. It says here, find a c value in the open interval 0, 9 for the given function that satisfies Rolle's theorem. Now, to use Rolle's theorem, we have to make sure that the hypotheses are met. Unfortunately, this is a simple parabola, and all parabolas and all polynomial functions, as far as that goes, are continuous and differentiable. So that's not a big deal. To be continuous just simply informally means you can draw it without picking up your pencil. You're not going to have some hole or gap or vertical asymptote, basically. Nowhere is there a place where you have to stop drawing and begin drawing again later. To be differentiable means that A, you're continuous. You have to be continuous if you're going to be differentiable. Also, there's no sharp corners, basically, or vertical tangent lines, though. You don't see a lot of those. For the most part, sharp corners are what you're looking for that will prevent you from being differentiable if it's continuous. But in this particular case, we need to check the endpoints for Rolle's theorem. And f of 0, if you look right here, f of 0, you should be able to tell is 2, because it's just going to be the constant. And f of 9, a quick check, 9 squared is 81, 9 times 9 is 81, 81 minus 81, 0 plus 2. So these match. They have to match for Rolle's theorem. They won't for mean value theorem, but they do for Rolle's theorem. Alright, so what we do is to actually apply it, you just simply find the derivative, which if you know anything about calculus, you know the derivative of y equals x squared minus 9x plus 2 is 2x minus 9. Set it equal to 0. Okay, so basically it's, as we've defined earlier, a critical value. And eventually x is 9 halves. And notice that 9 halves, or 4.5, is between 0 and 9. So you may, on occasion, find some points that are not between, but to satisfy Rolle's theorem, you need to be between. You need to actually be in that interval. Let's look at this to try to make some sense of it. So I'm going to go to Desmos right here and graph that. Y equals x squared minus 9x plus 2. And on Desmos, if you hit space, then this little brace, looks like that. 0, I'm going to come down here, less than or equal to x, less than or equal to 9. It draws that piece. And I'm going to zoom out a little bit. So for Rolle's theorem, what you'll always be able to do is connect the endpoints with a horizontal line. For this one, we found it to be 2. So y equals 2. You can see that green line there. That will always happen for Rolle's theorem. Mean value theorem it won't, but it will for Rolle's theorem. So what Rolle's theorem says is there's another horizontal line that's going to touch it between these 2 points that will be tangent to the graph. So in this case, it happens down here somewhere. It happens right down here at 4.5. And you can see on Desmos at the bottom of your screen, that's the y value, negative 18.25. So just to physically show that, we don't actually have to come up with a negative 18.25 if you're doing the problem, but just to show it, you connect the endpoints with a horizontal line, and there's another horizontal line that's tangent to it at a point between those endpoints. That's what Rolle's theorem says. Again, it depends on the fact that this should be both continuous. You can draw it without picking up your pencil, and there's no sharp corners or vertical tangent lines in there. Okay, so that's one example. Let's look at one with some trig in it. Give you a simple trig example. Let's go. Just did that one. Let's go to. Okay, y equals cosine of x minus 3 on the closed interval 0 to 2 pi. Now, cosine wave, if you do any kind of variation of it, if you mess around with this amplitude or its period or its phase shift or its midline or anything like that, it's still going to be a wave. Right? And waves have no sharp corners, they have no breaks, they have no asymptotes. So it's going to be continuous and differentiable. Therefore, we can use Rolle's theorem. And we can verify in this case that the cosine of 0, now these are radians, the cosine of 0 is 1. As you should know, just picturing the unit circle in your mind. 1 minus 3 is negative 2. Cosine of 2 pi, now 2 pi of course is the same place on the unit circle. So cosine of 2 pi is likewise 1. Again, make sure your calculator's in radian mode if you're using it. 1 minus 3 is negative 2. So because these match, we can use Rolle's theorem. So we find the derivative. The derivative, here it's in the notation y, so derivative of y with respect to x is negative sine x. Of course, the derivative of 3 is 0. So I set that equal. And we can go ahead and trash that negative because I divide both sides by negative 1. It goes right into the 0 there. And technically, this requires an inverse sign. And the calculator is probably going to tell you 0, which is a problem because 0 is an endpoint. We need it between the endpoints. But again, applying a little simple trig and realizing that on the unit circle, if you take one revolution around the unit circle, you're going to hit y coordinate 0 on the far left, which is radian value pi. So pi is the answer that we want here. And again, we can show that here. Let's do that quickly. So same thing, decimos y equals cosine x, was it minus 3? Doesn't really matter. Yeah, it was minus 3. So we're just going to lower that midline down a little bit. Doesn't matter. Let's just bring it on in. And remember, on Desmos, you can go space, you can go brace, 0. I'm just going to say less than straight from the keypad. It won't make a difference here. It is technically on the closed interval, but again, that's not a big deal. Desmos, you can type pi for pi. So there's a nice picture here. Again, I can draw that sort of that upper bound y equals negative 2 here. So again, the endpoints connect nicely. So there should be a point somewhere in between. It just so happens both our examples, that endpoint was exactly halfway between. That's not always going to be the case, but it is here. So that happens at y equals negative 4. And again, the negative 4, you don't have to. That's not the answer. The answer is pi at the point pi negative 4 right there. I'm just trying to illustrate what Rolle's theorem is saying. It's saying if you can connect those endpoints with a horizontal line, there must be some other place where you can be tangent in a horizontal line. One more quick example for this, and again to summarize, be clear here. To answer this question, you're going to want to say this, so that they're equal in the endpoints. You're going to want to mention that it's continuous and differentiable, and then you just find that value where the derivative is 0. And ensure that that value is in fact between the endpoints. So this, pretty well everything it says from here on down. Looks like I misspelled theorem too on there. Fix that. Alright, so this last example, sorry, let's go back. Last example, do this again. What about this one? Find a value in C, value C in negative 3, 2 that satisfies Rolle's theorem. Now, this is an absolute value function, so it should immediately, get your math senses going, or set off an alarm in your head. Something about that absolute value function is V-shaped. All right, so when you're V-shaped, that's a sharp corner. That's no good. And if you actually find the derivative of the absolute value, you have to break it to its definition, to the piecewise look. And the only derivatives you're going to have here, a part of it's going to be 2, for part of it's going to be negative 2. It's not ever going to equal 0. So at first you might say that contradicts Rolle's theorem, because if you put negative 3 in here and 2 in there, it gives you a nice